Hello. Today we are going to see how the natural frequency simulations are performed on the induced draft fan radial impellers. So in the previous session we had performed the structural simulation and arrived at the stress and deformation results. And we also found that the stress values were uh, very much in limits compared to the yield strength of the material. So we had the stress values as 41 Newton per mm square and the deflection values as 0.05 millimeters. So now we concluded that the structure is safe and stable. However, these kind of structures that are subjected to repetitive loadings or cyclic loadings or induced to an atmosphere where there are heavy vibrations experienced. So in such cases, we need to study the extended parameters, like how the natural frequency, the forced frequencies are going to influence on the structure. So normal mode simulations or the natural frequency is nothing but the fundamental frequency of the structure. Now the structure is made of mild steel, and the mild steel has got its own material properties, and the arrangement of domains within the steel, I mean the mild steel plates, are to be considered. So based on the material properties, we try to visualize how exactly the domains are arranged within the solid plate structure. So these are thickly packed, tightly packed domains, and it is isotropic in nature, and where the arrangement of the domains are similar in all the layers. And since it's tightly packed, let's try to visualize the configuration. So this consists of molecules and atoms, and let's get into the atomic structure. So within the atomic structure, we will notice that there is a nucleus with a proton and a neutron, and circling the nucleus there are electrons in each orbit. So we have different kinds of shells, K, L, M and N, and then there are distribution of electrons, and each electron has got its own attractive and repulsive power. So electrons are generally E minus. So these electrons revolve around the nucleus, and at any point these electrons will never get into the nucleus or merge with the nucleus, which means that the atom does not exist. So these electrons in various orbits, the K, L, M and N shells, all orbits, the spin of these electrons are considered to be the vibration of the structure. So this is a vibration that takes place when the structure is completely at rest. Even if the structure is at rest, it is freely suspended. The internal domain arrangements or the internal movements of these electrons or the spin of these electrons will cause vibration. So this is what we call as the natural vibration of the structure. So it depends on the geometrical parameters like the thickness, etc. And it also depends on the Young's modulus, Poisson's ratio and the density of the material. So based on this, there are certain mathematical calculations, and performing these calculations, the natural frequencies are extracted. So we know that angular velocity omega is equal to square root of K divided by M, which is the stiffness divided by the mass. So already we have calculated the stiffness parameter from the earlier simulation, the structural simulation, where the force matrix F is equal to the stiffness matrix K multiplied by the displacement matrix X. So F divided by X will give you the stiffness parameter, or vice versa. F divided by the stiffness parameter K will give you the displacement. So we consider what is the stiffness from that, and we put it inside this particular equation. Omega is equal to square root of k by n. Omega is nothing but 2 pi by t. So omega is 2 pi divided by t, and that can be written as 1 by t multiplied by 2 pi into square root of k by m. Okay, so 1 by t will be frequency. Okay, so from that we can find out the inverse. So the frequency can be determined will be 1 by 2 pi square root of k by m. Okay. So now with this particular formula, the frequencies, the fundamental frequencies are extracted: F1, F2, N1, N2 and N3. These are the fundamental frequencies. This is how it is denoted. Now once it is extracted, this is to be compared to the forced frequency. So that is the next set of calculations, simulations, where the structure is subjected to the operating condition. The operating condition is, say, 800 rpm. So the angular velocity omega will be equal to 800. So by calculation, we will be able to find out the normal modes, the fundamental frequencies. So here we have performed the fundamental frequency simulation, and that fundamental frequency has got 10 modes. So we are extracting 10 modes, and we'll see what are the 10 modes here. So here we'll find that the first frequency, the second frequency, third, fourth, fifth and sixth, all 6 frequencies are 0, and the 7th frequency is 250.9 or 231 hertz. The 8th frequency is 318.4 hertz. The 9th frequency is 330.1 hertz. So here you find how the impeller is responding to each frequencies. So you will be able to clearly visualize it from this. So this is how it behaves when the frequency is 330. So that is the third frequency, and the second frequency is 318.4. That is the second frequency, N2, and then N1 you have 250.9. So these are the 3 different possibilities of a vibration to occur, and these are the mode shapes. You know, the vibrating shapes, how the impeller will respond to that particular frequency. So in the lab, what we do is we try to make use of tuning fork, and then we have a resonating column, and on the resonating column we touch the tuning fork, and then we check for the vibrations. Okay, so now that is how the calculations are done. Okay, and similarly we also have different other test apparatus that will be able to help us determine the normal modes or the natural frequency. So here these 3 modes, the 7, 8 and 9, starting from 250.9 hertz to 330.1, are the first 3 fundamental frequencies of the impeller, the induced draft fan radial impeller. Okay, now what we are trying to understand is what is going to be the significance of finding out these 3 modes, why we are finding out the normal modes. So actually what happens is, when the system is completely at rest, so this particular normal mode simulation is when the system is completely at rest. That is, the impeller doesn't rotate; it is static. It is simple, it's simply suspended. So at that particular point, there are these 3 set of, the 3 sets of frequencies that we have. And now, when this impeller is subjected to a rotation of 800 rpm, okay, that is the operating condition. So at operating condition, we will extract what are the normal modes, not the normal modes, the modes. So there we go for the boundary conditions. So we have already seen in the stress analysis that these bolt holes are all constrained, and we have applied a rotation of 800 rpm at the shaft central axis. Now that was the input what we have given for structural simulation. So the same input is applied onto this by keeping the omega value, the angular velocity, as 800 rpm, and then we perform the analysis. So that will be the next step of analysis, the force frequency analysis, and we check, is there any frequencies which is matching to these three frequencies. If it is matching, then we call it as a resonance, and that is the frequency where the structure can collapse or fail. So here in the animation you are able to see that the contours are extending from the edges, from these two diametrically opposite edges, which means that this is the region or the probability where the system can fail. So that is exactly the conclusion from our previous simulation. We mentioned that the region where the materials are very less, okay, that is the region where the material probability for the material to fail is fast. So from here the crack generates or propagates, because all the other regions are all perfectly welded to the vertical stiffeners, the blades. Okay, whereas here at the center it does not have any material, it's open. So diametrically the system can collapse. But what we have done in the previous optimization, the previous simulation, is we have introduced a crown in both top and the bottom. The reason for introducing the crown both top and bottom is to avoid this particular tear, so that it's a kind of tension reinforcement. We are providing a crown on the top, okay, so that the stresses, the tearing stresses, are distributed across the crown. So the probability for a failure is very less when there is a crown that is attached to the shroud. Okay, so this is the way the predictions are done, or the inferences are done. So now let's try to see an example. So the history says at some point of time there was a bridge made of metal structure, pig iron or wrought iron, and over the bridge there were a fleet of soldiers marching, and all of a sudden the entire bridge collapsed. And it was a mystery for quite a long time, and then later on the engineers, they found out the reason for that particular collapse. The soldiers were wearing boots which were reinforced with metal saddles, plates, and now that's for enhancing the march past. So this particular boot with which they were marching on the bridge created a frequency which was exactly equivalent to the natural frequency of the bridge, one of the frequencies of the bridge. So when these two frequencies overlapped, okay, there was a state called as resonance that existed, where the entire bridge collapsed. So which means two frequencies of equal nature or amplitude, when met together or combined together, it became a bigger amplitude wave, and the system crashed. So that is called resonance. So most of these structures will keep resonating. Okay, even self-resonation is not possible, even for that particular operating load, if it doesn't fail, but still because of externally induced vibrations or frequencies, there is a probability for the structure to fail. So these kind of structures are all some or the other way connected to the other structures which has got vibrations induced in them. So these structures can possibly fail because of vibro acoustics, maybe the vibrations because of structures. Okay, we call it as structural vibrations. Okay, so these kind of noises or these kind of vibration, whatever is induced from that, is called structure-borne noise. Okay, so now here these structure-borne frequencies are more than sufficient to clear off this particular system. So that is the reason what we do is in the next consecutive steps, we perform a random vibration. So before that, a forced frequency system is done, analysis is done. In the forced frequency analysis, we will apply the same boundary conditions, but then we will find out what are the frequencies. Now those frequencies, if it matches with this particular frequency, what you see here, that is from the normal modes or the natural frequency or the fundamental frequency, then the structure is sure to collapse. But if the frequencies are not matching, then the structure is safe. Then later on, what we do is the next step would be analyzing it for random vibrations. Because let's see, like if there are some vibrations, some 2 or 3 different machineries operating in around that zone, and all these particular machines are all connected to a single base, a metal frame or structure, and now that structure is more than sufficient to transfer vibrations from one machine to the other machine. So that is nothing but induced vibrations. So now here in this particular system, if there are any induced vibration, now that also is to be checked. So sometimes there will be some repetitive loading. So cyclic loadings of these structures can be subjected to cyclic loadings. Now because of that cyclic loadings, okay, the structure will experience a lot of stresses. So every cycle there will be some stress, and that stress gets accumulated, and because of over accumulation of these stresses, that will lead to some fatigue, and because of fatigue there can be a failure. And that is one of the reasons, like any product designed, okay, for the industrial purpose or for any purpose, there is a durability check done. So the system has to be checked for durability, and we need to simulate and find out whether the system is going to be durable, and if it is going to be durable, for how long it is going to sustain, what is the sustenance of the structure. Okay, so now let's conclude here and revise like what exactly we did here. This is a normal mode simulation or the modal frequency simulation, where the fundamental frequencies are extracted, and we have 7, 8 and 9 here in the tabular column as the frequencies. This is the first natural frequency N1, this is N2, and this is N3. Okay, and from the previous episode, from the structural deformations, we found that the structure was safer from the stress as well as the deformation perspective. So the next episode will be focusing on forced frequency or forced responses. Okay, so let me once again conclude by saying, please subscribe and share this particular video to as many people as possible. So let them also go through this and try to understand what exactly are the industrial principles and processes involved in the simulation, and how a complete product design and development phase digital simulation is going to enhance the system. Okay, so thank you very much for your patience, and please feel free to comment and put your valuable suggestions, and all your suggestions are welcome, and we can definitely work on any of the queries, and we can make the system more interactive. So thank you very much.